I'm Reverend Greg and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. In this video we'll continue with learning how to blur an image. But as always, a short disclaimer first. This tutorial series is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths, so if you see any mistake in my video or see a better way to solve a problem, please add a comment so everyone can learn from you. In the last video, we created a single pass blur shader. First we used an isolated kernel where all pixels contributed to the final color by the same amount. Then we created a shader with a smooth Gaussian weight so the pixels closer to the current fragment weigh more than the farther away pixels. And to increase the blur, we learned we need to increase the kernel size. The main problem with this shader was its performance. In this example seen here, the shader has to take 225 color samples for each fragment, which is a tremendous amount of samples per frame, so it's time to optimize. And this is the first and most important step in optimizing a blur shader. Instead of rendering everything in one pass, we render the same image in two passes. A horizontal blur pass and a vertical blur pass. The order doesn't matter, by the way. If we do the second pass on the result of the first pass, we'll get an image blurred equally in both directions. And here lies one of the reasons why the Gaussian equation is so well suited for blurring. The two-dimensional equation is just a squared one-dimensional version. Meaning if you do one pass with a one-dimensional horizontal blur and a second pass with a one-dimensional vertical blur, the result is exactly the same as doing all in one pass with a two-dimensional blur. But let me show how this works in an image manipulation program like GIMP. Let's say this is what we want to blur. Now let's simulate the first pass blurring this vertically. And now horizontally. As you can see, the result is a nice and smooth blur in all directions. So by blurring just one direction first and then the other, we need to take a lot less samples. In this example of a 15 by 15 kernel, we just need 30 samples instead of 225, which is a huge difference. In a smaller kernel like 7 by 7, the difference would be less dramatic, but still considerable. 14 samples instead of 49. And in a larger kernel like a 31 by 31 kernel, it would be tremendously more. 62 samples instead of 961 samples. The downside is we need to set up surfaces and draw the image twice instead of once, which costs a bit more performance. But even for small kernel sizes, it's an improvement in performance already. Before I continue explaining the blur we're creating today, I'll quickly need to explain something about the application surface. This is the documentation on the application surface. The main steps are marked bold. GameMaker Studio sets the render target to the application surface just before the draw begin event, and resets the render target just after the draw end event. So everything we draw in draw begin, draw and draw end event is drawn to the application surface. And everything we draw in post draw or any of the draw GUI events is not going to the application surface. Then right before the draw GUI begin event, the application surface is drawn automatically to the screen. Technically not to the screen, but to the back buffer where the screen pulls the image from, but I just think of that as drawing to the screen. So everything we draw in the post draw or any draw GUI event is being drawn directly to the screen instead of the application surface. And this order is important for post-processing. When we talk of post-processing shaders, what we basically mean is applying a shader to the whole screen. And doing this in GameMaker Studio is very simple. First, in some create or room start event, we're telling GameMaker Studio to not automatically draw the application surface after the draw events by calling the function application surface draw enable and setting that to false. Then we draw everything to the application surface in the draw events as usual. And after that, in the post-draw or any draw GUI event, we can set up the post-processing shader and draw the application surface to the screen. So with that clarified, let's have a look at multi-pass blurring. While in the last video we blurred sprites, in this video we're going to blur surfaces. There's 3 reasons why I do this. First, we couldn't do this double pass technique with sprites only anyways. We need at least one surface. Second, we're going to use blur as a post-processing effect, and post-processing is all about surfaces anyways. And third, this being a tutorial series, it's time to learn something new. So here's a visualization of what we did in the last video. We had a sprite and we drew that through the single pass shader to the application surface. GameMaker Studio then automatically draws the application surface to the screen. This time we're going to draw the sprite without a shader to the application surface, as we would do with every tileset, object or sprite asset in a game, but we're not letting GameMaker Studio draw the application surface to the screen automatically. We're manually drawing the application surface to a second surface, blurring one direction only. In this example, the horizontal blur pass. And finally, we're going to draw this surface instead of the application surface to the screen, doing the second pass through the shader, in this case the vertical blur pass. But now let's apply this knowledge to our test project in GameMaker. First, let's duplicate the shader from the last video. That was the 1-pass Gaussian discrete sample shader. I'll call the new shader Shader 2-pass Gauss discrete. And let's also copy the last video's object, which was called Object 1-pass Gauss discrete, rename the duplicate to Object 2-pass Gauss discrete, and place it in our test room on the main layer as well. In the last video, we used the blur shader to draw a sprite blurred to the application surface. This time, as mentioned, we'll draw everything normally to the application surface, and in the end, we'll draw the application surface blurred to the screen. So in the room editor, we can just set a single sprite mockup, which pretends to be our game with all its objects. To do that, let's turn off the tile layer we usually use as background, and instead use the background layer at the bottom to draw the Mage City single sprite mockup. We'll just pretend this is our game, and in post-processing, we're going to blur the whole game. Now inside the create event, I'll set the info text for the base project as usual. And since we're not blurring a sprite this time, we can remove the sprite blur line. And of course we need to set the newly created shader here, Shader 2-pass Gauss discrete. In the last video we used the UVs of the sprite to calculate texel size and to clamp the samples to the UVs of the sprite. But since we're post-processing a surface now, we won't need any UVs anymore. The surface's UVs always range from 00 to 11, and the samples are clamped automatically. But now that we're blurring in 2 passes, we'll need to tell the shader which direction to blur, vertical or horizontal. We could do that by creating 2 shaders, one for a vertical blur and one for a horizontal blur, but I decided to go for another option. Instead of 2 shaders, we're creating just one and pass in the blur direction with a 2-dimensional vector. The vector 1, 0 will be used to blur horizontally, and the vector 0, 1 to blur vertically. So let's replace the uniform UVs with the uniform blur vector. And of course we can now also remove the 2 lines we used to get the UVs. Next we need to change image width and height, which are not that of a sprite anymore, but that of the application surface or the GUI, depending on what you're doing. The way this base project is set up, both are the same, and I'm getting the width and height of the GUI. And to make that clearer, I'll name the 2 variables GUI width and GUI height. Then the texel size can be simplified as well. We already know the surface's dimensions in UVs are 1 in both directions, so the texel size is just 1 divided by width and height. And finally, we need a surface for the second pass. For reasons getting more obvious in a later video, I'll name that surface Surface Ping. As explained earlier, when post-processing we don't want GameMaker Studio to draw the application surface. We want to control that manually. So we need to disable that feature by calling Application Surface Draw Enable. Now of course this causes a problem with the 2 modules we created in the last video. the automatic application surface drawing disabled, they won't draw the application surface anymore even if they are selected. So I'm just going to tell those two modules to draw the application surface in Draw GUI Begin event if those modules are selected. But back to our new 2-pass Gaussian module. Whenever working with surfaces, never forget to freeze surfaces somewhere. In GMS2 we can use the cleanup event, and in GMS1 you'll use something like destroy, room end or game end events. And this is also a good place to re-enable the automatic drawing of the application surface, or this would stay turned off when switching to another of our test rooms. Now on to the draw event. We won't need that anymore to apply the blur. We'll need to do the post-processing after the normal draw events. But for the base project we still need an empty draw event to not draw the module placeholder sprite. So let's just copy the code in here and write a description only. And then create a Draw GUI Begin event and paste the old draw code in here. Now inside the if statement, but before setting the shader, we'll need to prepare the ping surface where the first blur pass goes. We'll check if the surface exists, and if not, we'll create it. Size simply is the GUI width and height variables from the create event, which in our setup are the same as the application surface. And since we're drawing every pixel there and have no alpha, we don't need to clear the surface after creating. And after setting the shader, we can now remove the line where we passed in the UVs. And of course, we can also remove the draw sprite line. That's just a leftover from the last video. Now for the first pass. This will be the horizontal blur drawing the application surface to surface ping. We need to set the blur vector to tell the shader to blur horizontally. So as mentioned before, we pass in the normalized horizontal vector 1, 0. Then we can set the surface target to surface ping, draw the application surface to the upper left corner of the target, and reset the target. So now we got a copy of the application surface on the ping surface, but it's horizontally blurred. That's the first pass done. Now to the second pass, where we draw the surface to the screen or back buffer and blur it vertically. For the second pass, only the blur vector uniform changes. So we'll just pass in the normalized vertical vector 0, 1, draw the surface ping, and then reset the shader. This will automatically draw the surface to the back buffer and not to the application surface, because we're in a Draw GUI event. Now let me quickly change the corner info text. The kernel stays the same. We won't need kernel squared. In the last shader we got the samples per pixel from this, and that's different now. So we can replace kernel squared with samples per pixel. In a 2-pass blur we'll take samples twice the kernel size per pixel, once for the horizontal pass and once for the vertical pass. Instead of kernel squared, it's 2 times the kernel size now. And samples per image now is samples per pixel times the GUI width and height. Now I'd like to add another info. How much better this is than in the 1-pass shader regarding the samples taken per pixel or image. So I'll compare the number of samples taken in the 1-pass blur with the samples per pixel in this version. That's it for the Draw GUI Begin event, but for testing purposes, let's just temporarily add a line after resetting the shader for now. Draw surface, surface ping, 0, 0. And change the blur vector when drawing to surface ping to a vertical vector 0, 1 instead of 1, 0. So when we run this, we should just see the vertical blur. Now to the shader. We won't need the vertex shader and can move to the fragment shader right away. Here we can remove the uniform's UVs since we don't use the UVs anymore. But we'll need a uniform vec too for the blur vector. Next, since we don't calculate horizontal and vertical at the same time, we need to change the Gaussian equation from the 2-dimensional to the one-dimensional version. We'll still call the function weight, but now it takes a float instead of a vec2. And from the equation we'll just remove the x's and the pos y's to turn this into one dimension. The main function needs some changes too. First, the offset is not a vec2 anymore either, but a float. Total weight and kernel can stay as they are. But the for loop doesn't need to be nested anymore. We're not doing two loops like in a single pass shader, we're doing one loop per pass now. That's the whole purpose with switching from one pass to two pass after all. So let's remove the inner loop. And in the remaining loop, we'll just remove .x from offset because it's a float now. Inside the loop, sample weight and total weight stay the same. The sample line needs to change though. First, we don't need clamping since we're working with the surface, so let's remove that. But we'll need to tell the shader which direction to take samples from, and to do that we multiply the offset and texel size by the blur vector. So if we pass in a blur vector 1, 0, this means offset and texel size will not affect the y-coordinate. And so the y-coordinate added to VV-text code will always be 0, which means we're only taking samples offset on the x-axis. And if the blur vector is 0, 1, we're only taking samples offset in the y-axis. Once again, if you have some trouble understanding this code, I'd recommend to watch the video Introduction to GLSL Part 2 in this video series playlist. After that, you should have no trouble understanding this line. The rest of the shader remains unchanged, so let's run this for the first time. Now don't forget, for testing purpose, we had set the draw event to only show what's on the ping surface, and we had set a vertical blur vector when drawing to the ping surface. So if we select this module and increase the kernel size, we'll see a vertical blur. Now let's go back to the draw GUI begin event and change the blur vector in the first pass back to a horizontal vector 1, 0 and run the program again. Now we can see the horizontal blur. And again, back in the draw GUI begin event, let's just remove that line with the test draw and run this once more. And now we can see the two-pass blur. Just play around with kernel size and sigma a bit. Kernel size will increase the blur size, but also increase the number of samples taken per pixel. Now before ending this lesson, I'd like to add a small improvement to the shader code. At the moment, we're calculating the weights of both sides, left and right, or up and down. However, those weights are just mirrored copies, so we can improve the code a tiny bit by looping not from the left to the right, but instead take the center weight and then loop from the first step to the last step and taking the samples left and right of the center within the same loop. So let's do that. In the fragment shader, we first take the center sample and store that in our blurred color right away, instead of setting that to a 0 vector as before. This also means the total weight needs to start at 1 instead of 0. As learned before, the simplified Gaussian equation we use always returns 1 if offset is 0. So we can set total weight to 1. Now we need to shorten the loop. Instead of starting from minus blur steps, we start at 1. And inside the loop, we copy-paste the sample and blurred call lines and just change the operator in front of one of the offsets to a minus sign. So this will take a sample left of the center, and the other line takes a sample right of the center. But since we're taking two samples in one for loop, the total weight needs to increase for two samples as well. So we'll just multiply the sample weight by 2 on the total weight line. So now the Gaussian equation is running only about half as much as before, although of course we're still taking as many samples as before. So this is just a minor improvement. Let's run this to confirm everything looks as before. We can easily compare this with the one-pass shader and it should look the same still. Also, if we now compare this version with the last at a kernel size of 65, we can see a huge difference in performance. With the 1-pass shader I usually get around 20 FPS on my machine, and with the 2-pass shader I'm at a steady 60 FPS. And now I can also show you the difference on my tablet. When I did this in the last video about blurring in 1-pass, we got horrible frame rates of about half a frame per second or worse at a kernel size of 65 by 65. But switching to 2-pass blurring improved that by a lot. But still not good enough yet, so we need some more improvements which we'll cover in the next videos. Just one last thing before ending this video. I tried to Google for this series and it's still difficult to find. With all the countless hours of work I put into this, I want everyone who wants to learn more about shaders to find this tutorial series. So I read stuff about search engine optimization, and apparently some of the most important factors are the number of subscribers to the channel, the number of thumbs up, and the number of comments. I know I said I don't care about that stuff, but with that knowledge on search engine optimization, I kinda do care now. So if you like this series, please subscribe, give thumbs up to the videos and add a comment once in a while. And rest assured, I still have no plans at all to monetize this channel. I don't plan to earn money on YouTube and I'm quite happy with the job I already got. So that's it for this video. We just greatly increased the performance of our blur shader, and in the next video we'll improve that even more by using the GPU's ability to interpolate textile colors at nearly no additional cost, letting us decrease the samples needed by nearly half again. It's going to be a bit more complicated than this video, but I hope I'll be able to explain the technique with some nice sheets I prepared. I was really excited when I had the maths correct, which took me ages sadly, and I hope you'll be excited as well. Until next time.